Okay, so looking at mole to mole ratio. So you've had some time to kind of review the concept of a mole. Mole to mole ratio, we done like balancing equations and predicting products. Well, let's we're going to use all those skills in stoichiometry, this unit. Let's kind of just think of a non-chemistry example for this. So let's say we're making a grilled cheese. My product, the thing that I'm making is grilled cheese. And if you're making a grilled cheese, let's assume that you use 2 slices of bread for every 1 slice of cheese. So thinking of like balancing your equation, you have 2 slices of bread here. Like if this was unbalanced, you'd have no number there. You'd have bread plus cheese equals sandwich. But over here, you have 2 slices of bread. So if you were like counting your atoms and stuff, that's why you need a coefficient of 2 here. And then you can see there's just 1 single slice of cheese. So that's why there's just a coefficient of 1 there. Okay? Now, solving some problems, like let's say you're you own a grilled cheese restaurant place thing, right? And you want to know, all right, if I want to make 7 grilled cheese sandwiches, how many slices of bread do I need? Now, a lot of you could do this in your head, and that's fine, but trying to understand this concept of a conversion factor is very helpful to like solve some of these chemistry type problems you're gonna have to do in this unit. So how it would work was, start with, this is what you know. Start with what you know. You know you have 7 grilled cheese sandwiches, so 7 grilled cheese. Now your conversion factor, you get this ratio here, you get this from the balanced equation. Okay? From the balanced equation, right? The two slices of bread for every 1 grilled cheese sandwich you make. And when you're doing the review of mole stuff, you could think of this as over 1. And because these are on opposite sides of the fraction, the grilled cheese cancels out. So the unit that you're left with here is bread. So then you multiply across the top. So 7 times 2. 7 times 2 is 14. Divided by 1, divided by 1. Anything divided by 1 is just itself. So 14 slices of bread is what you need. Now again, you could have done that in your head, most likely, but understanding this method is important for understanding the idea of a mole ratio. So getting into like a chemistry example of a mole ratio, let's say we have our balanced equation where we have hydrogen gas, so H2, plus oxygen gas, so here's O2, and you make H2O. Now, I'll actually write the equation unbalanced over here. So it would look like that. To balance it, you would have 2 hydrogens, 2 oxygens. Here you got 2 hydrogens, it's a goofy looking 2, and 1 oxygen. So that's why I have a 2 as my coefficient there. So that would give me 2 oxygens, 4 hydrogens, and then the 2 for H2, that's because you need to get 4 hydrogens over here. So the equation is balanced, so 2, 1, 2. Okay? What that's saying is if you want to make 2 water molecules, you need 2 H2s and 1 H2O. Okay? So we're going to use this balanced equation. This is going to give us our conversion factor. So we're going to solve some problems using this. And kind of another way to visualize this mole ratio is if I make the molecule here like sulfur plus oxygen and we make sulfur trioxide, I need 2 sulfurs. Like think of like it's almost sort of like a recipe, or like that first example, the grilled cheese, right? 2 sulfurs for every 3 oxygen molecules. And when you do that, you will make 2 SO3s, 2 servings of sulfur trioxide. All right, so looking at a problem of what this would look like, they're telling us in the reaction we have H2 plus O2 gives us H2O. So the same reaction we just did. So first step is you have to balance the equation. That's why I have spaces there. And we just did that, so I'll just copy that over. You have 2, 1, and 2. So that's your balanced equation. And then they ask us if 3 moles of H2 are used, how much water forms? Well, always start with what you know. Kind of like what you did with the moles. We know we have 3 moles of H2. Okay? And you can put it over 1 if you would like. And then we have this stoichiometry map that we're going to be using throughout the entire unit. This isn't going to be that helpful for today because all we're doing today is just focusing on the mole ratio. But I left it here just so you can see kind of where we're going to be building towards. We're using grams of X X and Y and all that. Those are referring to different molecules. Basically how we can convert from different things. So here, don't really worry about this bottom right thing for today, but just kind of, just so you're not confused why that's there. Anyways, whatever the unit is here, you have moles H2, you need this unit to go down here. So moles H2 goes down here. And then what goes up top here, that is what you want to find next. So we're trying to find how much water forms. And by much, we're staying in the same unit. We're staying in the unit of moles. So moles of H2O, you're like kind of using this. X could be your H2, Y could be your H2O. So then put in the numbers. You get the numbers that go here from your balance equation. That's why we did so much work balancing equations. That's why you have to balance the equation here. I have a coefficient of 2 in front of the H2, so it's 2 moles of H2 for every 2 moles of H2O. Okay? So then, units cancel, moles of H2 cancel, moles of H2 cancel, and our ending answer, what we wanted to find is how much H2O. So moles of H2O is our answer. So you'd have 3 times 2, multiply across the top, and then divide across the bottom. So 3 times 2 is 6, divided by 2 is 3. So 3 moles of H2O. And you might be thinking, well, that's the same answer as H2. And the reason it's the same answer is because they have the same ratio. We make the same 2 moles of H2O for every 2 moles of H2. Because in other words, if the coefficients are the same in the balanced equation, if this was 7 moles of H2, you would make 7 moles of H2O because they're the same ratio. Really, we're just doing ratios here. So let's look at, we call this the mole ratio right here, just to be sure. So let's look at another example. We have PbNO32 plus Ki gives you PbI2 plus KNO3. So we got to balance the equation first. So let's, my reactants, I got 1 lead. Now you see nitrate here and here, so we can keep those together. So 1 nitrate, or I'm sorry, you got 2 nitrates, and the reactant's got 2 there. You have 1 K and 1 I. In your products, you have 1 lead, you have 1 nitrate, 1 NO3, and 1 K, and 2 I's. So we need to fix the NO3s and then the I's. So let's fix my NO3s. I'm going to need a double KNO3 to get 2 NO3s. That'll get my K to 2. But then if I come over here, well, I'm going to need to fix my K's. Oh, okay, cool. If I just double KI, that'll get us all balanced. Okay, so unfortunately we're not done. We just use that to get your balanced equation. So then now, if I give myself some space, start with the number they give you. They say if 3.23 moles of Ki are used, so write 3.23 moles of Ki. Okay, put it over 1. The unit here is what goes here. So moles of Ki goes diagonal. Okay? And then what are we trying to find? We are trying to find how much lead 2 nitrate. So lead 2 nitrate, Ki is what we had here. Lead 2 nitrate is going to be what we have right here. So moles Pb NO32 is what goes there. So to figure out that ratio, so to figure out the numbers that go here, you get these numbers from the balance equation. So I have, there's no number that's essentially a 1. It is a 1. So you have 1 mole PbNO32, and then you have a 2 in front of there, so 2 moles of Ki. So your answer would be 3.23 divided by 2, which is 1.62. 1.62 moles of, these cancel, so moles of lead 2 nitrate, PbNO3 2. Okay, so there you go. And that's really, that's it, so you got the worksheet with some extra practice on it, but it's really important that you kind of get a good foundation with that, because then we're going to build upon that next class to do what you see here, going from a gram to a particle, or from a particle to a gram.